what we do in the next few decades, in some ways, this is like one of the most consequential times to be alive in, you could argue in the history of animal life, because what we do in the next few decades really will leave a legacy in the fossil record, essentially forever.
CO2, carbon dioxide. It's a molecule we hear a lot about in the context of climate change. It's in the air we breathe, it's released as we drive our petrol cars and used to make plastic bottles. And it's being pumped into the atmosphere faster than ever. But what actually is CO2? Where does it come from? And why is it causing our planet to change so drastically? That's what we're going to be finding out about on The Climate Question from the BBC World Service with me, Greer Jackson. But I can't answer those questions alone. So I've asked a couple of experts to help me. A familiar face to our regulars is Esme Stallard. She's a BBC climate and science reporter and handily studied geology at university, which, as you'll find out, is very relevant to today's topic. Hello, Esme. Good to see you.
It's great to be here. My favourite topic, as you say, geology. So I'm delighted.
Geology rocks, as the old adage is. Peter, that's what you're in for today, Esme. Peter Brannan is an award-winning science journalist and contributing writer at The Atlantic. He's also written a book called The Story of CO2 is the Story of Everything. Hello, Peter. Thank you so much for joining us.
Thank you so much for having me.
Any geology-related jokes for us?
Oh, man. It's still early in the morning over here, so maybe I'll think of one by the end of the podcast.
Now, Peter, your book is as thick as a brick. I mean, how long did it take you to write that?
It took about 5 years from proposal to finishing it.
And did you enjoy writing it?
It was great being able to, I get to do a tour of a coal mine, which isn't everyone's idea of fun, but for me it was. Got to go to Death Valley to investigate the coldest time in the history of the entire planet, this thing called Snowball Earth, which kind of ironically you can see the vestiges of in this, the hottest place on Earth today. And this is a climate catastrophe hundreds of millions of years ago that is intimately tied to changes in CO2 in the atmosphere as well. So yeah, it was great.
Now, you've set us up really nicely, Esme. We need to talk about what exactly is CO2, carbon dioxide, this molecule that we talk about all the time in climate change.
Yeah, so I'm going to do my best to be a sort of chemistry teacher for the next minute. So CO2 is a compound, and each molecule has one carbon atom and two oxygen atoms, as you'd expect, CO2. And it occurs naturally as a gas on our planet at the pressures that we experience, or if it's very, very cold, which is unlikely to be this cold, but minus 80 degrees, then you can get it occurring as a solid.
And it makes up a tiny portion of the atmosphere, doesn't it? I think that's so surprising to a lot of people.
Yeah, I think when we talk about the concentration of CO2 and it's sort of increasing quite significantly, we think, oh goodness, it must be some sort of 90%. But actually, that's not the case at all. Air is made up of oxygen, CO2, water vapour and other gases, and it's only a very tiny, less than 1% of that. But actually, those very small changes in CO2 can impact the way that our planet functions, which we'll probably get into.
Yeah, I mean, Peter, less than 1% is mind-boggling, given the impact that it does have on our planet. But I mean, maybe to illustrate that, let's just talk about what our planet would be like if there was no CO2.
If the atmosphere was suddenly stripped of CO2, the temperature would drop by something like 60 degrees Fahrenheit in a half century. So you'd probably drop into this thing, Snowball Earth again, which I mentioned, which is when the oceans freeze to the tropics. And all life on Earth would die because photosynthesis would stop, because all life on Earth is carbon-based, and the source of that carbon is ultimately CO2, which plants and algae and plankton take in and then turn into this organic living matter, and then that feeds the rest of the biosphere. So it's a good thing that there's some CO2 in the atmosphere, enough to feed plants and keep the planet from freezing over, but not too much to, launch you into this kind of greenhouse planet, which occasionally the planet does veer into. And as a point of reference, in the past 50 million years, when CO2 has been 0.1% of the atmosphere, there have been palm trees and alligators in the Arctic Circle. And when it's been a little less than 0.02%, there's been an Antarctica's worth of ice on top of North America, and sea level was more than 400 feet lower than it is today. So this is a really, really narrow window that the planet kind of miraculously does navigate through these big, huge biogeochemical cycles over thousands to millions of years, which is kind of a miracle that you know the planet stays within this nice habitable range for us, except for freak times in Earth history when you have big mass extinctions and kind of what we're doing today. We're starting to see sort of the glimmers of the symptoms of some of those kind of scarier events when CO2 gets out of control.
I guess, given everything you've just said about the power of CO2 and how it can mean, just a tiny fraction of a percentage can mean palm trees in the Antarctic or, glaciers over much of Europe. Esme, it does make me wonder, what is it about CO2 that traps the sun's heat?
So energy is transferred in the form of waves, and it's how we get the sun's energy. It comes in as infrared. Now, depending on the type of wave, we can get different, basically more tightly packed or more spread out waves. So, for example, microwaves have a different length to, say, X-rays, and infrared's the same. Now, what CO2 does is it interacts with the infrared wave, and because it has 3 atoms, it's able to sort of twist and manipulate and rotate and interact with that infrared, and it absorbs it and then it radiates it back out to our planet, effectively trapping the heat in. Now, the reason I mention the different lengths of those waves is because there are some compounds, so for example, oxygen, which only has 2 atoms, which doesn't interact with infrared. Effectively, it just passes straight through, but it prefers waves that are much tighter, more tightly packed. And so oxygen doesn't interact with it at all. Now, there are other parts of our atmosphere, for example, water vapor, which does interact with infrared in the same way that CO2 does, as in it's able to interact with it. But the difference with water vapor is that it's itself kind of changing in reaction to that. So as water heats up, it evaporates, it then rises, it gets cooler, it condenses, and it rains out. So even though when it interacts with that heat, there are short-term changes, CO2 hangs around for a lot longer, so sort of over 100 years. And so that means that as we're adding more and more CO2 into the atmosphere and it's interacting with that heat from our sun, it's effectively like adding more and more layers onto yourself. So like adding an extra vest every time we're kind of pumping CO2 in there. And that is why CO2 reacts with infrared, but other things in the atmosphere like oxygen don't. And this is absolutely crucial, as Peter said, to make sure that our planet is habitable. Without it, it wouldn't actually be possible for us to live on planet Earth. So it's a very useful process that goes on, but that also means that sometimes when there's too much of it, we can kind of get overheated, a bit like wearing an extra, coat, for example.
We've talked about the sources of CO2 so far, which is when we're not around, putting it out into the air through smokestacks and tailpipes. It comes out of volcanoes, but there's also all sorts of natural sinks for it as well. So we mentioned earlier that plants take it up and basically are the foundation of the entire biosphere and the rest of life on Earth. That sort of carbon moves through until it's exhaled as CO2 again. And then there are really long-term geological sinks for CO2. So while it comes out of the Earth's crust, it also eventually goes back into it. There's this really long time scale sink for carbon, which is that when CO2 reacts with rainwater, it makes it more acidic. And when that more acidic rain reacts with these things called silicate rocks, so things like granites and basalts, they're chemically transformed, and the products of that reaction eventually get washed out into the rivers, then into the ocean, and ultimately, things like oysters and coral reefs and kinds of plankton that build their shells out of calcium carbonate will precipitate that and fall to the bottom of the ocean and eventually become limestone. So on the really long term time scale, like in hundreds of thousands of years, all the CO2 we're putting into the air right now will eventually leave the system as limestone or things that ultimately might become coal, oil, or natural gas. It's just that those processes take so long and are kind of just irrelevant to the scale that we're putting it out now. We're just overwhelming the system by putting it in much faster than these sort of natural sinks can accommodate it.
As you say, what's happening today is really far from natural. And some scientists have called this era of climatic and environmental change the Anthropocene. I mean, do you want to come in here, Esme?
Anthropocene, with the sort of that term you refer to, that geological period, as we look back through Earth's history, what geologists do is they say, okay, where are we seeing significant changes in the way that our planet functions or life on Earth? And they will give a term to that because there are sort of boundaries marking it. So it might be, for example, a period where there is particularly, a lot of dinosaurs, for example, and that might define it. It might be the particular temperature that might define a geological period. But there's a marker in the record, in rock record, to say, okay, we've had a significant shift here. And what has been the proposal is that we call this the Anthropocene, because the human impact is so significant on our planet that we might see that in the geological record. And that's in different ways. So one is the types of rocks that we might start to see, what is laid down in our oceans because of the CO2 concentrations, but also other things like we might start to see increasing concentration of plastics in the geological record because of our waste. Now, at the moment, the International Union for Geological Sciences, the body that sort of gets together and say, is this a new period in our Earth's history we need to define? At the moment, they haven't agreed to call it the Anthropocene, but I think that reflects the growing body of evidence of the overwhelming impact humans are having on the history of our planet.
And when exactly would the Anthropocene or climate change begin if it was decided by, the various societies and science?
We're sort of in a weird scenario where they would probably define it pre-industrial revolution, where we're starting to see if we're going kind of more on the climatic changes, where we're starting to see a real ramp up in CO2.
When is the pre-industrial revolution?
So yeah, exactly. So sort of early 1700s, sort of moving in 1750, sort of then onwards, and obviously that ramped up quite significantly.
Just to pick up the thread a little bit from what Esme was saying, one of the reasons why it's so controversial about whether, when to start the Anthropocene is because, you talk to archaeologists or even some paleontologists, and they will tell you that human effects actually go back tens of thousands of years. Global ones like megafauna extinctions and the spread of agriculture, which totally transformed the face of the planet. But then things really do hit this inflection point with the Industrial Revolution. And by being able to tap into fossil fuels, basically all the plants that have ever been buried over the entire age of animal life over the last 500 million years, European society and eventually, conscripting the entire world was able to tap into this basically unlimited source of ancient plant energy that just totally took off the constraints of how much energy you could use at the surface of the planet. And so obviously since, around 1850, we've totally transformed not only the atmosphere, but the environments around us and even the chemistry of the ocean. And it really does hit another inflection again after 1950, when the technology and oil exploitation capacity that was developed during World War II was basically hit overdrive after World War II. And you see this other inflection point that's sometimes called the Great Acceleration, where you see increased deforestation and overfishing and things like that. So there really just is this explosion of human activity powered by these fossil fuels.
Yeah, I mean, Peter described this really nicely in his book, but effectively, fossil fuels are natural plant matter. That's what they are. It over time becomes either coal is one example, or oil and gas. And what we're doing is in burning it, we're re-releasing that carbon. Now, of course, that has formed over millions of years, and suddenly we're releasing it very, very quickly. I think Peter describes it in his book as an explosion of planetary energy, and I think that's a really good way to kind of sum it up what's happening there. And of course, that's, benefited human societies quite significantly. It's enabled us to kind of accelerate through scientific developments. It has contributed quite significantly to the increase in wealth of economies. I think at the same time, and we've talked about this before on the podcast, is that the fact that we kind of haven't managed to monetize or sum up the kind of negative consequences of utilizing those fossil fuels, that kind of when you have this explosion of energy, actually what you're doing is you're tampering with the climatic system, and also more locally, you're kind of putting in extra pollution into the air, affecting air quality, affecting health, which also has significant economic impacts, not to mention the impacts on our own lives. And, I think sometimes that isn't compared equally. But I think it kind of alludes to the fact of why it's difficult to kind of move away from fossil fuels because of that economic impact that it's had in such a short space of time.
So we've heard how CO2 makes up less than 1% of our atmosphere, but that it's vitally important in keeping our planet habitable. But now, the rate at which humans are pumping CO2 into the sky is unprecedented. It's causing our planet to warm and fast. The last 10 years have been the hottest on record. So to understand what might happen next, scientists look for clues in fossils, in glaciers, hidden in the soil, to tell us what our planet was like in the past, and therefore what it might be like in the future. Now, last year in 2024, CO2 hovered at around 424 parts per million. So, Peter, when was our planet last thought to have similar levels? And what was it like then?
So the last time CO2 was around 420 parts per million was a little over 3 million years ago in this period called the Pliocene. North and South America weren't connected by Panama yet. There were red pandas and rhinos in Tennessee, and there were forests in the Arctic with camels in them. So this is a totally different world. CO2 is about the same, but sea level is about 70 feet higher, and it was about 3 to 4 degrees warmer than our planet. So that's a long time ago. It's before the evolution of our genus Homo, which shows up around the start of the Pleistocene, which is the last 2.5 million years or so of when we've gone in and out of these ice ages and then warmer interglacial periods, they're called, which is like what we're experiencing today. But the Pliocene is a really long time ago. So we would expect that if we hold CO2 sort of indefinitely at this level of over 400 parts per million, that you might start to see changes on that scale. It would take centuries to millennia to actually melt the ice to raise sea levels that much, but it just shows you how out of equilibrium the system is right now and sort of where it would be happy at this level of CO2. So we're really transforming the planet in ways that are outside of the, not just human historical memory, but the evolution of Homo sapiens this is outside of our sort of climate window. Once you melt ice sheets, then you're actually changing the albedo of the planet. So literally the color of the planet. If you lose an ice sheet in Greenland or in West Antarctica and you cover it in grass or even forests, if it gets really warm, that's darker and that will absorb more sunlight and that'll warm the planet up more. And so if you keep CO2 high for really, really long time periods, you can really transform what the planet looks like and the temperature of the planet. Luckily for us, if we suddenly stopped emitting all CO2 tomorrow, a lot of that CO2 would be reabsorbed by the Earth, and we wouldn't keep it at that high level for millennia. While CO2 has been different levels than it is today, the rate of change in CO2 today is almost unprecedented in the age of animal life, really. Occasionally, you do get huge injections of CO2 into the atmosphere and oceans from these mind-bending volcanic events that happen once every 50 to 100 million years. But even those are thought to be about 10 times slower than what we're doing today. So we really don't know what we're doing. And that's sort of the stuff that keeps me up at night about climate change, is that you do have these analogs in Earth history, but in some ways what we're doing doesn't really resemble anything.
I mean, Esme, as a geologist, is this something you've looked at, these sorts of analogs?
Yeah, I think it's the speed that Peter's talking about, which I think really worries geologists, because what you do as a geologist is that you look in the historical rock record, you say, okay, as Peter said, last time it was at this temperature, this is what the outcome was. And that's fed into a lot of climatic models. So when, the reason we talk all the time about 1.5 degrees is because what geologists are saying, and when they run these climate models, is they say, well, last time we were at that temperature increase, we know that this is what the planet was doing in terms of weather. And so that's kind of our best guess on what might the outcome be. But there is always that caveat with the speed situation that Peter's talking about. And I think the best way to explain it is that if you were in a car and you were driving and I asked you very slowly to put your foot on the accelerator till it reached the floor, you might get to, 500 meters down the road. Now, I ask you to put your foot to the floor suddenly and I will see how far you get. Now, your foot is still to the floor, but you're doing it a lot quicker. And so you're reaching that, you're potentially pushing it even further. And I think that's what people are worried about, is you're pushing the planet beyond what it's used to doing in terms of adjusting to that increase. There's very few examples in the geological record we can draw from where we can say where we've added this much CO2 this quickly, we're going to see this change. So when geologists say last time we were adding this much, temperatures were 3 to 4 degrees higher, they were so many the sea level rise was so many tens of feet higher. Actually, what we might get is we might push the planet so quickly that its natural mechanisms that it does to try and sort of adjust and rebalance to a kind of comfortable level actually might be kind of overwhelmed. And then you get these runaway effects. And this is where we talk about tipping points, and we've kind of discussed that previously. But it is absolutely the speed that I think it's very hard to get your head around. We're sort of talking 200 years versus in most cases we've seen sort of 2 or 20 million years where we've seen these increases happen before.
And to me, it's also not just the speed, right? It's also the timescales that we're talking about, the impacts that we're going to be having, thousands, millions of years in the future, Peter.
Yeah, so one of the reasons why I originally sort of had my imagination fired by this topic in general, sort of this deep time perspective on climate change, is that, um, you know, oftentimes climate change is talked about as, it's just this theoretical thing on computer models and it's all, it's in the future. But I really had my mind blown by being shown by geologists who had drilled this sediment core from the North Atlantic Ocean, and they pulled it up and you have this chalky layer laid down over hundreds of thousands of years. And then suddenly it goes red for, a meter or so. And then it goes back into chalky sediments again. And they could point to it and say, this was a warming event 56 million years ago, in some ways similar to, the amount of CO2 we might ultimately put into the atmosphere. And you can see the oceans acidified. So this is what happens when CO2 reacts with seawater. They get more acidic and makes things that build their shells out of calcium carbonate, chalky things like oysters and some kinds of plankton and things. It makes them harder to stick around. And you actually see that acidification is what they're looking at in this layer of sediment in the bottom of the ocean, drilled from the bottom of the ocean in the North Atlantic. And so that was just so evocative to me that we might leave a similar layer. If you're a geologist 60 million years from now, from who knows what branch of the tree of life, but you go and drill a sediment core in the middle of the ocean, you might be able to point to a similar layer and say, look, this species transformed the chemistry of the entire planet enough to leave this mark in the seafloor sediment. So what we do in the next few decades, in some ways, this is like one of the most consequential times to be alive in, you could argue in the history of animal life, because what we do in the next few decades really will leave a legacy in the fossil record, essentially forever. And depending on whether we're wise and can navigate this painful transition well, things will reflect better on us in the fossil record than if we really don't do a good job of getting off CO2 and mitigating the environmental effects we're having on the planet.
I mean, Peter, the key difference between the periods that you and Esme are describing in the rock record is that today we are humans and we have agency. We can do something about this if we choose to.
So in some ways, we do resemble the first glimmers of sort of these cataclysms that you do see in the rock record, but we're also totally different than a volcano or an asteroid, in that this one has a steering wheel, hopefully, and we can avoid steering the planet towards what we know from the rock record. If you go down this road too far, can lead to some really catastrophic conclusions. So that is ultimately the I guess source of hope, is that human beings are incredibly adaptable and clever and resourceful. And throughout our history, we've lived through lots of ice ages, and it took, we didn't survive those because we had thick hides or fangs or anything like that. It's because we had human culture and technology. And so that really is where the hope is for the future, is that by organizing ourselves in more adaptable ways and developing technology, we can avoid what we know from this legacy in the rocks are some nasty endpoints. So that is what I hope for.
Peter Brannan and Esme Stallard, thank you so much for joining us on The Climate Question.
Thank you so much for having me.
Thanks for having us. Great to be here.
And thank you for watching. Don't forget to subscribe to the BBC World Service YouTube channel so you don't miss out. And if you have a climate question of your own, then write it in the comments below and we'll answer it in a future show. I'm Greg Jackson, and we'll see you next time.